Thanks everybody. Yeah, so like Aaron said, I'm here to talk to you about MAVEN. So I gave this talk the title of the MAVEN Mars Space Weather Report. I'm going to talk a little bit about space weather, which is all this junk here in yellow that the sun spits out toward all sorts of planets, including Mars. But really, I think this talk is about what the MAVEN mission is about, which is understanding this climate mystery on Mars. So I don't know if you've got a chance to be outside today, but I think we would all admit that it's very habitable today on the planet Earth. I certainly found it to be very habitable. But I don't think you find the same thing to be true on Mars. Right? Mars is a barren desert wasteland where you pretty much instantly die. So not like Boulder today. And as far as we know, it's inhabited only by robots that we sent there. Yeah, this is one of my favorite pictures returned by, this is the MER rovers, so not Curiosity, but the earlier rovers. And this gives you a sense of how empty Mars really is. And as we've looked, but so far there's no evidence for life there. There's no conclusive evidence that life ever was there. But there is evidence that life maybe could have had a chance to get started there, and that's what MAVEN's about. So these rovers, the only inhabitants of Mars that we know about, are there to understand the history of the planet. Mars is a really unique place because it's so desolate, because its surface is so old. And so what's reported on Mars is the earliest part of solar system history. On Earth, we have plate tectonics and vegetation which cycles all this rock. But there's a record on Mars that stretches back almost to the very beginning of the solar system. And that's what these rovers have explored and showed us that the early solar system on Mars is very different than what you have today. So on Mars today, there is water, but it's mostly present as ice. This is a picture of a crater near the North Pole of Mars taken by the Mars Express spacecraft. So there is ice exposed at the surface in places on Mars. There's also CO2 frost, or dry ice, exposed at the surface. But liquid water is extremely rare on Mars today. It can flow perhaps for short times at the surface in certain places, at certain times of year when the illumination conditions are just right. And that's what you see here on the edge of the crater. These slope streaks, as they call them, are now pretty well understood to be caused, at least in some cases, by flowing liquid water. There's mineralogical evidence that indicates that these streaks couldn't be formed by any process other than water flowing out on the surface. So you can get liquid water on the surface of Mars today, but you can't get it for very long. And that means that any life which exists on Mars today would have to be buried pretty deep in the surface of Mars. That stands in contrast to abundant evidence from the early history of Mars that water flowed. And the slide is cut off a little bit, but ancient rocks tell us that Mars is much wetter than it is today. So this is Ebers-Waldy crater on Mars. You can see this beautiful delta formation with braided channels, multiple episodes of deposition, and this looks very reminiscent of a river delta on the Earth. So we know that water flowed on the surface of Mars long ago, but the fact that there are large craters impacting the surface tells you that this happened a long time ago, more than 3.5 billion years ago. Life was just getting started. Besides the morphological or shape evidence that we have for water flowing on the surface of Mars, there's also abundant mineralogical evidence. So these guys here are called blueberries. Maybe a lot of you have heard of these. This was sort of a hallmark of the Mars Exploration Rover mission. When they took a picture of these, they looked blue in the filters they used. Because they're a little spherical and they looked blue in the original picture. They called them blueberries. These are hematite spherules that only form when you have water percolating through rock. That concentrates iron and magnesium over time into a little nodule, which when the rest of the rock erodes, is left behind. And if you ever have a chance, you can go see these for yourself on Earth in canyonlands and arches. They're all over the place. So that's a great analog site, is what we call it, for the the weathering processes and the chemical processes that produce these styles on the Earth from Mars.
What's that circle?
Yeah. So this is from the Mars exploration rovers, and you remember the Curiosity has a drill to drill into the surface. The best they could do with the MER rovers is give them a little Brillo pad, like spin around at the surface and maybe clear a little bit of this dust off. Because all of this stuff that you see here, all this red, is dust and a rind that's grown on the surface of the rock over the last 3 billion years since it was put in place. With Curiosity, you may have seen pictures where they can actually drill into the surface. And it turns out rocks on Mars are red only for like the first quarter inch of the rock. And they turn gray really quickly. So this was an attempt to brush this off and maybe get at the rock underneath. Because all they had was a little pad. They couldn't get very deep. So this leaves us with this big mystery, right? We've got abundant evidence on the surface from shape characteristics of riverbeds and deltas and minerals that could only form with flowing liquid water. But today Mars is a barren wasteland where no water can flow, right? So we have this picture of a transition which may have occurred on Mars from a warmer, wetter, more Earth-like planet, perhaps a habitable planet where life could have started, to the cold and dry desert that we know today. And the question is, could this have happened? Is there a way to get the atmosphere, which would have been required to support all of this liquid water, to disappear? There's 2 options when you're trying to get rid of an atmosphere. To be very basic, right, you can put it down into the surface as rocks, or you can put it up into space and get rid of the atmosphere by escaping it all into vacuum. So people have gone back and forth for decades about which of these is more likely. But here at LASP, and especially on the MAVEN team, we think there's a really good case to be made for loss to space. And one of the big reasons for that is the size difference between Mars and the Earth. So you see here the Earth and Mars to scale. Mars is a small planet, about half the diameter of the Earth. It's about 1/10 the mass of the Earth. So gravity on Mars is much weaker than it is on the Earth. There's this really nice, NASA likes to shop around this fact that if you try to play basketball on Mars, you play it with hoops that are 3 times as tall. So you can imagine 30-foot tall basketball hoops because of the low gravity of Mars. And that low gravity applies everywhere throughout the atmosphere, right? So if you've got atoms and molecules in the Earth's atmosphere, they're going to stick around and bounce around and be held in by gravity. But in Mars, those same atoms and molecules with the same velocity will go much farther and potentially escape the planet entirely. To understand what causes this escape, we need to look at the sun. Because all of that energy that the atoms and molecules have in the atmosphere ultimately derives from the sun. It comes from photons in the extreme ultraviolet. It comes from the solar wind, which is composed of particles, protons and helium nuclei that have restricted their electrons and flow out in a constant stream. It comes in the form of magnetic field, which is carried by the solar wind outward. And it comes in the form of periodic intense outbursts of solar energetic particles. So what you see here is well, for one person it's noise, for another person it's signal. But all this static here is the result of solar energetic particles impacting what's supposed to be acting as a camera on the spacecraft, but is actually acting like an energetic particle detector. So these 4 solar influences can give energy to the atmosphere of Mars and can produce enough energy and enough velocity in the atoms and molecules of the atmosphere that they can escape. This energy is all deposited in the upper atmosphere. So if you think about the sun and where it's going to deposit its energy, that's going to depend on the wavelength of the light that's coming from the sun. We all wear sunscreen when we're outside, or the dermatologists tell us to, because of ultraviolet light, which penetrates in small fractions to the surface. But it turns out most ultraviolet light is absorbed much higher up in the atmosphere, at altitudes of hundreds of kilometers. And at these really high altitudes, when that high energy light is absorbed, it can heat the atmosphere and it can produce ions. It can strip electrons out of molecules and atoms. and produce what we call the thermosphere and the ionosphere. Thermosphere because it's hot, and an ionosphere because there's ions there. And that's what MAVEN is designed to measure on Mars. We need to measure not only the solar influence, but also we need to get into the thick of things to measure how the atmosphere is responding. So we do that in a variety of ways. We measure directly with direct detection instruments, and we measure remotely in the ultraviolet. Because as you might imagine, when you shoot ultraviolet light into a planet, a little bit gets scattered back out. So by looking at the ultraviolet light that gets scattered back out of the atmosphere of Mars, we can infer things about the properties of the atmosphere. So that's the justification for MAVEN. We have a planetary mystery. We know that the atmosphere is capable of escaping, and we know that that escape is driven by the sun. So we need to go to Mars, and we need to measure the atmosphere, and we need to measure the sun. And that's what the spacecraft is designed to do. We have 9 instruments, which are pointed out here. The spacecraft itself, from wingtip to wingtip, is about the length of a school bus. Pretty substantial. And these big solar arrays, as you might imagine, produce a good amount of drag when you get down into the thick of the atmosphere. And that's why we have these gull-wing solar arrays. They're bent just a little bit, because even though MAVEN is orbiting at hundreds of kilometers in altitude, the air is very thin, it produces a substantial amount of drag that we have to take into account the aerodynamic forces. The instrument that I mostly work on is down here. That's the imaging ultraviolet spectrograph. And I'm going to be presenting a lot of results from IUVS, which is the closest thing that MAVEN has to a camera. But I'll try to not give short shrift to the other instruments, which after all do a much better job of telling you what's there as opposed to giving you some brightnesses which you then point to a model. So these are the instruments. Of these instruments, IUVS was built here at LASP, and EUV was built here at LASP. The others were built as part of a collaboration with other institutions on the MAVEN team. These cloaked figures in the background here are the principal investigator and the people who actually built the instrument. I did not get to build the instrument. They would not let me into the room with the instrument because the instrument would not work if I came near it. The closest I ever came to the spacecraft was about 50 feet behind a glass wall at Lockheed Martin before they locked it in a shipping container and shot it as far away from me as they could. So these are all the sort of graduation photographs of all of the instruments before they get sent for integration onto the spacecraft. It's a really capable payload. We have instruments which measure ions and electrons. We have instruments which measure photons, either from the sun or from the atmosphere of Mars. We have instruments which measure solar energetic particles. So instead of just looking for the noise in our camera images, we actually have detectors which are designed to see these things. We measure the magnetic field of Mars, which is extremely important in controlling how the atmosphere escapes. We make the first measurements of potential in the atmosphere of Mars in the Viking mission. And we have a neutral gas and ion mass spectrometer built by the same folks who built the one on the Curiosity rover on the surface of Mars, but this one gets to orbit high up and give them a high up perspective on the same atmosphere. We launched from Cape Canaveral, Florida. I did get to see it launch. And then we were on a ballistic cruise to Mars. You can see here that getting from Earth to Mars is kind of tricky. You have to launch from Earth when Mars will be where the trajectory will hit 6 or 9 months from now. So that's what we did successfully. You can see that almost 3/4 of a year passed from the time of launch to the time when we arrived at Mars. And during that time, most of the instruments were very unhappy because they were not inside an atmosphere measuring it. But since I work on a remote sensing instrument, we were pretty happy because you can do remote sensing from anywhere. There's no sensing like remote sensing. When we got to Mars, we almost immediately had a change of plans. And that's because a comet was on a collision course with Mars. Okay, not quite a collision course, but in astronomical terms, this comet did a close flyby and buzzed Mars so close that the planet was within the extended coma of the comet. This is something that has never happened before, and people calculate that it's a once in 50,000 years or once in 100,000 years event, depending on what you believe about the orbits of comets. So really rare, and there were thoughts at the time when this comet was first predicted to get this close to Mars about, oh, should we delay the mission? What should we do to protect us from this gas and dust that's going to be coming at Mars at many kilometers per second? Because even if a tiny grain of dust hit the spacecraft, we would be completely obliterated, or an instrument could be completely obliterated at those speeds. But we did launch, and we took a picture of it. When we got to Mars, in the commissioning phase, just before this comet hit, we were able to point our spectrograph at it and take a picture. Now, we're operating in the ultraviolet, and we're operating at basically dial-up internet connection data speeds back and forth from the spacecraft. So I'm sorry that this picture of the comet that we were able to make is not quite as brilliant as this ground-based image. But we do retain full spectral information in UV, which is something that you can only do from space. And we were able to get some good science out of this about the extent of the hydrogen in the comet's coma. That's what you see here. And almost all of this signal here is due to gas surrounding the comet that you just can't see invisibly. What you see here is ice and dust that's been blown off of the comet, mostly as a result of that gas evaporating off of the nucleus. So you're seeing a small fraction of the picture invisible. You can see much more in the ultraviolet. So I mentioned that we worried about what would happen to the spacecraft, and ultimately it was decided to use the planet as a shield. So pretty much every spacecraft orbiting Mars at the time executed maneuvers, fired its engines so that it was behind Mars from the point of view of the comet when the comet came by at closest approach. And on MAVEN, we went into what we call a hunker down mode. We couldn't call it safe mode because that's already a thing. So we had to come up with a new name, and the one that we settled on was hunker down. It's not safe mode, it's hunker down mode. And that meant that we were not taking science observations at the moment of closest approach. But very quickly after, through an enormous effort by people at Lockheed Martin to get the spacecraft back up and running, to boot it up from scratch, we were able to take observations and see what happened when this huge cloud of gas and dust flew by Mars. Now, to explain what we saw, I need to first give you an idea of what the Mars atmosphere looks like normally. So this is what the Mars atmosphere looks like without a comet flying by. This is data that we gathered before the comet flew by, when we were still gathering science, before we hunkered down for the comet pass. And what you see here is wavelength on the horizontal axis versus intensity or brightness on the vertical axis. So we do spectroscopy with IUVS, breaking light up into its component colors. Here's a little gas lamp that you can get with hydrogen gas on the inside. You put an electric current across it and it emits light. So neon does this too, and it's orange. When hydrogen does it, it's this sort of bright purple. But if you put that light through a prism and spread it out into its component colors, you see that, well, really your eye is a very poor optical instrument. It's not purple at all. It's a combination of red and blue and this deep dark blue, dark purple here. So that's what we do here with our instrument. The spectrograph splits the light up into its component colors so that we can get a sense of how bright the Mars atmosphere is at a bunch of different wavelengths. And you see here atmospheric emissions which are due to certain chemical species or molecules in the atmosphere of Mars. So we see this bright feature here results from ionized CO2. CO2 is the major component of the Mars atmosphere, and when you hit the Mars atmosphere with ultraviolet light, you pick an electron off of one of these CO2 molecules, and then it scatters sunlight right at this wavelength. You also see these emissions resulting from CO. These are the result of a lot of things, including electrons just slamming into the molecule until it emits a photon. And then over here you see oxygen, which is a trace species in the atmosphere of Mars. So these are all things that we expected to see. These are things which have been seen since the early Mariner missions, which flew by Mars in 1971. So we saw this and we're like, okay, Mars still doing what we expected to do. And when the comet flew by, we saw a very different picture. And for many hours after the comet flyby and after we were able to gather data, we saw not gas in the atmosphere of Mars, but metal burning up as dust grains entered the atmosphere. So that's what you see here. This brightest feature in the atmosphere of Mars is ionized magnesium from tiny dust grains blown off of that comet, hitting the Mars atmosphere at tens of kilometers per second and vaporizing on their way in, producing a cloud of magnesium gas and ions. You see neutral magnesium here and iron here as well. And we saw this everywhere we looked for days after the comet flyby. That's illustrated here. The whole atmosphere of Mars was glowing in a layer around pretty much the entire planet, the result of this dust coming in to the atmosphere and vaporizing. Over time it faded, and we don't see it as often anymore. But when we did see it, it would have been amazing to see with your eyes if you were standing near it. Because for each of those dust grains that produces magnesium in the atmosphere, you would have seen a shooting star. And this is a woodcut from the Meteor meteor shower in 1833. Tens of thousands of meteors per hour filling the sky. And at Mars, you would have seen the same thing if you were looking up when this comet passed by. Unfortunately, Mars is inhabited only by robots, so nobody was there to experience this. I mentioned that we still see magnesium in the atmosphere today. That's shown here as a function of time. This is the brightness of magnesium plus that we see in the atmosphere, ionized magnesium resulting from dust shooting into the atmosphere and burning up. Here, just after we got into the orbit, is the comet at huge values of 500. Here, the units don't matter. 500 brightness. And down here, much lower brightnesses that we see almost continuously in every single orbit. And that's because space isn't quite empty. It's full of interplanetary dust grains. And Mars is basically plowing over these interplanetary dust grains in its orbit, scooping them up, so that we see this magnesium burning up at about the same altitude all the time. And when you look at the variations in these meteor streams and the brightness of the vaporized dust that we see in the atmosphere, you can do things like ask, well, does Mars experience periodic meteor showers like the Earth does? And does the Mars atmosphere respond in the same way that the Earth atmosphere does? And how many meteors are hitting Mars per second? That sort of thing is what this data will enable us to do once we're finished analyzing. We don't just look at the atmosphere and see magnesium. We also taste the atmosphere and taste iron in this case. So this is data from the neutral mass spectrometer. We're not always able to go to altitudes where this metal is being deposited in the atmosphere, but very occasionally we can go in deep dips and dip down to a much lower altitude than we usually get to. That's where these metals are vaporized in the atmosphere. And that's what you're seeing here in detector counts versus altitude on the inbound and outbound leg of the orbit. So the spacecraft is zooming in towards its lowest altitude and then zooming back out away from its lowest altitude. And during that time, they see nothing really, and then a little bit of iron, and then it goes away. And they see iron of two different isotopes, with two different amounts of neutrons. And that's in exactly the ratio they would expect for iron being carried on dust grains in the interstellar and interplanetary medium. And they can see iron. We could also see iron remotely, but they can see amazing things like chromium and manganese and all the essential ingredients for a healthy breakfast that IVS cannot see in the ultraviolet because they have mass discrimination. They can look at every single element in the periodic table one by one.
What are the units on altitude?
The units on the altitude are in kilometers. So here we got a little bit below 130 kilometers altitude. Typically we stay up higher at around 150 kilometers altitude. I think everybody on the team would love to get to 130 kilometers and 100 kilometers and flow on every single orbit. But if you do that, the engineers come back and they say, your spacecraft's going to burn up. I'm sorry, science just doesn't justify that. On previous missions, they did go lower, but some of our instruments are so sensitive that they couldn't deal with the densities of those low altitudes. The drag, even at 130 kilometers, is significant enough that we need to perform engine burns before and after every single maneuver, and that takes fuel. So that's ultimately what limits our ability to get down to these altitudes. Even at 150 kilometers, the drag won't let us stay there forever. So eventually, many years from now, NASA willing, we will circularize the orbit with a minimum altitude that's much higher so that we don't experience any of that drag. A lot of spacecraft orbit at 300 kilometers altitude, and there you don't have to worry about much. We get much lower. I mean, we raise all kinds of hell for the people who figure out whether or not there will be any collisions between spacecraft around Mars, because we go through so many altitudes on every orbit. They have to think about, oh, well, is MRO going to be in the way? That would be bad.
Yeah. And expensive.
It would be very expensive. So not only do we detect the dust when it's being ablated in the atmosphere, but we can also detect the dust when it hits the spacecraft. And that's because we have these long booms, which are normally there to detect electric fields in the atmosphere of Mars. But when a bit of dust hits the spacecraft at tens of kilometers per second, it creates a vaporized cloud of ions, which produces a spike in these instruments. So they see here voltage on their instrument as a function of time, and pop, a little dust grain just hit the spacecraft and vaporized a little bit of the spacecraft. And by looking at these dust signatures, we can again constrain how many meteors are hitting Mars at any time as a function of season. Okay, I want to switch gears and talk about Aurora. The title of the talk was the Mars Space Weather Report. So, I mean, unless you consider Comet space weather, I haven't really talking about space weather very much. What I mean usually by space weather is solar wind impinging on the atmosphere of a planet, and that's what happens in the aurora on the Earth. You have particles from the solar wind, which are channeled along magnetic field lines toward the north and the south pole of the planet, creating the northern lights of the aurora borealis. These are signatures of the deposition of energy into a planetary atmosphere. One of the things that MAVEN's really interested in is whether this energy deposition is driving the atmospheric escape. So one of the things that we're keen on is detecting aurora. At Earth, the aurora is confined to the northern latitudes because we have a magnetic field which is only open at these high latitudes. Particles which try to get in through here feel a force, and the entire magnetosphere is acting like a force field to prevent the particles from getting into the atmosphere. On Mars, there are also magnetic fields, but they're much weaker, and there's not a permanent dipole magnetic field like we have at the Earth that's generated by a core dynamo. So your compass is useless on Mars. Don't pack it for vacation. There's no GPS there also, so you're really going to have a hard time. Dead reckoning only. There is a magnetic field there, but it's all remnant magnetization. Sort of like when you rub a nail with a magnet, you can make that nail into a magnet for a little while, but then it decays away. The crust of Mars records remnant magnetization, which tells us that Mars probably had a field much like the Earth early on, but that field has since decayed away. The important thing from the point of view of aurora is that this field is open in many different places. What you see here is the probability that a field line is closed, so that where you see low values, so greens and blues, the field is open and particles can make it into the atmosphere. Where you see red values, the way is shut and particles can't get into the atmosphere. So you might immediately think, well, if the aurora on the Earth happens because the field's open near the poles, maybe we'll see aurora right here where the field's open. near, and you can channel particles in near these magnetic field lines. So maybe you'll see something like this. And for a long time, that's all that was seen, was aurora in the vicinity of magnetic fields that's maybe being focused a little bit by this magnetic field converging down and channeling particles in just where it's open. But we've detected aurora across the planet. So we call this this sort of confined aurora discrete aurora because it's small scale and it's localized in one place, and it results from particle energization at that location. We've discovered a new kind of aurora with MAVEN, which we call the diffuse aurora, by analogy with the Earth. The way we discovered it is by looking at ultraviolet spectra on the planet. On the day side of the planet, you see this. This is what we saw before Siding Spring passed by, with emissions from carbon monoxide, CO2 plus, and oxygen. On the night side of the planet, we see something different. We see these spiky band features which result from the recombination of a nitrogen and an oxygen atom. So those recombine on the night side of the planet, and they're momentarily in an excited state. And then that excited state decays, and they emit a little bit of energy as a photon. So each of these bands here is a photon that is a particular transition in the nitric oxide molecule as it releases energy when it recombines. This is called chemiluminescence. So when you look at a candle flame, there's a little bit of blue inside the orange. That's what's happening there too. You get molecules that are releasing energy through electronic transition. So this is what we see all the time on the night side. This is what we see all the time on the day side. And when we detected the aurora, we were looking on the night side, but we saw the stuff we only see on the day side. So how can you get day side emissions on the night side of the planet? And the answer is you have to bring particles around and slam them into the atmosphere with about the same amount of energy as the sun delivers on the day side. So that's aurora. We observed this last December. This is pretty exciting because we observed it just before Christmas. We got to call it the Christmas lights. Why not? And this occurred for about 5 days. And it occurred these are basically the same places where they saw this discrete aurora near the crustal fields with Mars Express, but we saw it everywhere around the planet. So this is a map of Mars, latitude versus longitude. And you see the topography of Mars here with Valles Marineris, the Grand Canyon of Mars, Olympus Mons, and the Tharsis Complex. And here are all of the observations that we made during this time. We don't have any observations in the southern hemisphere at this time. But everywhere we looked, we saw aurora for 5 days. Since then, we've come down here where this red and blue indicate crustal magnetic fields, and we've seen the same kind of aurora that Mars Express saw so long ago in 2005. But this remains pretty unique to see aurora across the whole night side of the planet. And probably if you were there standing on the surface of the planet, you would have seen something visible. Only robots.
Was this started at CME?
Yeah, so that's the interesting thing, is that MAVEN is uniquely equipped to answer that question. Because we have instruments which measure the atmosphere directly and which measure the sun. So previously on Mars Express, they were more limited in their instrumentation. They had some particle detectors, but they didn't have the whole suite of particle detectors that MAVEN had. And in particular, we found that our aurora, the brightness of our aurora here, shown in the top panel, is really well correlated with solar energetic particles, which Mars Express couldn't detect. So those SEPs, which caused all that static in that video that I showed, are coming into the atmosphere over these 5 days, hitting the atmosphere of Mars, and generating auroral emissions. They're also causing a big response in the electrons near the planet, and in the solar wind we see a big disturbance. So this isn't a CME. This is a solar energetic particle event, so I don't think this was accompanied by the other things that you need to be a CME. But pretty cool to see the smoking gun of the particles that are making the aurora as you see them. This was a fun thing to detect because we reported our aurora and we're like, hey, we see this aurora, do you see anything? And we're like, what altitude do you see it at? We say 80 kilometers. And we said, no way, no particles can get to 80 kilometers. And then they looked at their data and these particles can get to 80 kilometers. We were right, our altitudes were right. We've seen over 4 events like this previously, and that gives us confidence that we're seeing a different sort of aurora on Mars than we see on the Earth, or a different sort of auroral scenario on Mars than we see on the Earth. The Earth, the aurora is confined to these high latitudes because of magnetic fields which focus the electrons in there. On Mars, you get the same sort of thing near closed field lines. So you have discrete aurora here and discrete aurora here. But on Mars, draped field lines from the interplanetary magnetic field allow access to the night side of the planet. Sufficiently energetic particles can get around this kink in the magnetic field lines and deposit their energy directly into the atmosphere across the whole night side. And it'd be really great in some future mission to park out here on the night side of the planet and look and see how the aurora changes. Unless you think that electrons are the only thing that penetrate into the atmosphere of Mars, the solar wind can actually penetrate directly on the day side in the form of protons. So you have a hydrogen, which has lost its electron, it's just a proton in the solar wind, streaming toward Mars. It turns out Mars is surrounded by a diffuse cloud of hydrogen gas. Occasionally, one of those protons can bump into a hydrogen and say, hey, give me your electron. I need it for business purposes. And then the proton becomes a neutral hydrogen atom and is immune to the effects of any kind of magnetic field which is built up around Mars until it hits the atmosphere and deposits its energy there. So it turns back into a proton, its electron is stripped away by the atmosphere. They say you're going too fast, we need your electron, that's fine. And so you see these same particles which you saw out here in the solar wind down near periapsis, near the minimum altitude of the spacecraft. Exactly the same energy coming from exactly the same direction, but somehow they've tunneled their way into the atmosphere by hitting hydrogen atoms on the way in. That's about 1% of the solar wind makes its way into the atmosphere that way. Nobody was expecting this, but wow, it just sticks out of the data like a sore thumb. Really neat discovery. Okay, so I want to talk about some of the first data that we got back from MAVEN. This is the stuff that I focus on. So when we first got to Mars, we went to this really big moving orbit, a 35-hour orbit that got us much farther away from Mars than we can get now. And in that orbit, we were granted permission by Lockheed Martin after everything was determined to have gone safely with the insertion burn to take observations. So I was able, with some colleagues on the team, to design a sequence that would map out all of the field of view around the planet that was available, around the spacecraft that was available to us. And as luck would have it, when we were given the word to turn on, and when the first image came down, this is what we saw in a bunch of different wavelength bands. So I was up really late. It was 4 a.m. by the time this data came down from the spacecraft. And we ran it through the code, and we saw, there we go. The burn worked. We were orbiting a planet, and we're able to make the measurements that we went there to make. So you see here, reflected sunlight from the surface of the planet, oxygen surrounding the planet. You can see in the composite that it extends a little ways up above the planetary surface. And hydrogen, in this huge cloud surrounding the planet. Hydrogen can get to much higher altitudes because it's a lighter atom than oxygen is, so it's less bound by gravity. And it's this sort of data that let us study the extended atmosphere of Mars and see how this oxygen and hydrogen are escaping today as neutral atoms. Okay, this is how it looked from the point of view of MAVEN. Everything you could see for a few hours before Mars left our field of view. So these guys here are cosmic rays or solar energetic particles, which are interfering with measurements. You know, well, it depends on whether you study solar energetic particles. So if you add up all of the data we took in this insertion orbit, this is what you get for oxygen and for hydrogen. Hydrogen is much more extended, and it's a much brighter emission. So you can see it goes all the way to 10 Mars radii from the center of the planet. And the sun is in this direction here, so what we're mostly seeing is the day side of the atmosphere scattering light towards you. For oxygen, you can see it extends above the surface of the planet, which is indicated with this red circle here. This is all thermal oxygen that's at the same temperature of the atmosphere. You can see this little fringe of hot oxygen, which is produced in the ionosphere as a result of chemical reactions. Some of that oxygen is on its way away from Mars, leaving the planet forever, as we watch it right here. But this data, in image form, is not enough to give us a good idea of how much is escaping. To get an idea of how much is escaping, we need to add all of the data up as a function of altitude. This is what my colleague Justin Dean did here. You can see this thermal oxygen here, and then hot oxygen extending all the way out to the highest altitudes we can observe in our orbit. They're really great to get higher, but those particle and fields people want us to sample the atmosphere every 4.5 hours. And Mars, lest you think that Mars is the only atmosphere that's escaping, we have really great examples now outside our own solar system of escape from exoplanets. So this guy here, GJ436b is its full number if you want to dial it up, is orbiting closer to its star than Mercury is to our sun. And it's bigger than Jupiter. And it's surrounded by this huge cloud of hydrogen gas, which is blowing off it at such a rate as to spread out into a huge comet tail behind it. So this is a really exotic scenario that we can see now with the Hubble Space Telescope. But the data are sparse and they're difficult to interpret. And the data, like the data we get from MAVEN, the entire atmosphere all at once, you can start to understand how these escape processes work. Okay, I want to talk about ion escape pathways briefly. So models predict two major escape pathways for ions. I talked about neutral escape as O atoms and H atoms. But ions can also escape Mars too. Ion escape is crazy because ions feel magnetic and electric fields, whereas neutrals do not. So this here is the cover of a science issue in which we published 4 papers. This is the result of a particle simulation where you throw an ion in around Mars and you just track it and watch where it goes. And so you can see that ions just have no idea what they're doing in the tail of Mars here. There's a general movement backward. But look at this polar plume of ions here. They feel the electric field that's embedded in the solar wind, and they're accelerated outward away from the planet. That's a major escape channel. Maybe 50% of the ions that are leaving Mars are leaving through that channel. And nobody had ever measured these independently because nobody had ever had the instrumentation to do it until MAVEN. And so we can replace this model picture of escape from Mars with an actual picture using real MAVEN data of ion fluxes moving away from Mars. You can see in these red arrows here, ions moving toward the tail of Mars, and ions escaping in this polar plume. The background here gives you an idea of where the solar wind is interacting with the Mars atmosphere, and this green is the oxygen of Mars, which you saw in the previous image. So this is pretty great, right? A model is only as good as the data that you use to constrain it. And we're gathering comprehensive data on escape from Mars now for the first time with the proper instrumentation to put it into this kind of coordinate frame and really understand the processes that are going on. We can also map it, right? So this is one way to map it in 2 dimensions. But you can map it in 3 dimensions using all the places that the spacecraft has visited over its mission so far. This is stuff that Dave Brain does. And you can see here looking down at the base side of the planet, he's taken little boxes where the spacecraft visited and colored them according to how much ion escape he saw. So predictably, because the ions prefer to go downwind away from the sun, there's not a lot of ion escape on the base side. But on the night side, you see much darker colors indicating that ions are escaping out the tail of Mars, much more efficient. Okay, I'm running out of time, so I'm going to skip over this thing. And just say, we can go back to it, but say that MAVEN is all about understanding this transition from what geologically we know to be a warm and wet planet, early on to the cold, dry desert. We're gathering lots of interesting data, not just about escape processes, but the data that we have are letting us understand those escape processes better than anybody's ever understood them before. Understand the response of the atmosphere to changes in season, changes in the properties of the solar wind, and changes in the solar energetic input, which allow us to understand how these planets evolve and how potentially all Mars-sized planets throughout the universe evolve. So I'm going to stop there and take your questions.
Is the amount of atmospheric loss that's still estimated around 100 grams per second?
Right. Yes. Yeah. So that's the best that that Dave Crane has come up with, 100 grams per second. So that's about a quarter pound. So in the press conference where we announced this, we didn't talk about a quarter pounder per second, which is a vivid image. 1 quarter pounder every second for 4 billion years. That's a lot of. Yeah.
We're trying to understand, the processes that happened several billion years ago, using measurements today.
Yeah.
But we know things like the orbital parameters, the geometry of the orbit has changed. We know the sun evolves. Things may have been different in the past. Is there a way to sort of fold that into the analysis?
Yeah. So that's a really good point, and it's something that I think everybody on the team has been worried about since day one, right? We have a couple things going for us. One is that the sun is not constant in time. We get periodic coronal mass ejections and injections of excess energy from the sun into the atmosphere. And those look an awful lot like what we think the sun looked like billions of years ago. So if you can understand the response to a major disruptive event today, that maybe gives you an idea of what things were looking like all the time 3 billion years ago. The second way to get a handle on that is to use global models like this model here and constrain them using the data that we do have over all of the possible solar inputs so that we have faith that the model is doing a good job of predicting what's happening. And then you can turn the crank backward and say, the model predicts that over 4 billion years we've lost this much. There's another way to do it, which is to use the isotopes in the atmosphere as a record of change. So think of hydrogen as an example, right? Hydrogen has 1 proton and 1 electron. But deuterium has a proton, a neutron, and an electron. So chemically it behaves almost identically with hydrogen, but it weighs more. And that means that it sticks around when the atmosphere escapes. So if you can look at how much deuterium there is in the atmosphere, you can get an idea of how much hydrogen has escaped over time. You can only do that if you know how much deuterium relative to hydrogen there was in the early solar system. But we have a good idea because the Earth hasn't lost much of its atmosphere, and Jupiter certainly hasn't lost much of its atmosphere. So those are 3 ways you can get a handle on the total loss. We're not to a total loss number yet. At the current time, and with the sampling that we had of the MAVEN orbit, we can say a quarter pound per second. But that's not expected to be invariant with all of these other parameters. And I think your question about the orbit is a good one, because we know that the tilt of Mars has changed over time. And that's something we'll have to work into the models as well.
We've heard many talks over the last decade or so, mostly from friends and colleagues at SWIRI here in Boulder, about the dynamical evolution of the solar system.
Yes, yeah, that's
And
really interesting.
They emphasize how, the solar system today is not dynamically what it was 4 billion years ago, and you have to factor that into your.
That's certainly true, yeah. And I know that, so when you run these models backward, you can predict accurately up to a point, just like you can predict the weather, what the weather will be like up to a point a few days from now. But eventually you run into chaos. So we can do that backward a couple 100,000 years. But before that, we can get a good idea of statistically what it will be like, right? That's the difference between weather and climate. We have a good idea of, on average, what Mars looked like billions of years ago. We don't know exactly what it looked like. Yeah.
Atmospheric composition, how does the current composition of gases in the Mars atmosphere compare to Earth? And if you project back with the data you have, back when water may have been around, how was the atmosphere different?
Yeah, that's like the multi-billion-dollar question. So I can tell you today, the atmosphere of Earth is mostly nitrogen and oxygen, right? 80% nitrogen, 20% oxygen. On Mars, it's 96% carbon dioxide. So it's toxic. Well, it's not toxic, but you would definitely suffocate because you didn't have any oxygen. It outcompetes the oxygen. And what remains is mostly inert gases like argon and nitrogen. So there's not a lot of free oxygen in the atmosphere of Mars. The oxygen in our atmosphere is produced by life. On early Mars, nobody knows for sure. And a lot of people have tried to make water on early Mars by pumping up the current atmosphere, but the models all have problems. Because if you take a pure CO2 atmosphere like we have today on Mars and you pump it up enough that you get enough greenhouse warming to make liquid water at the surface, CO2 wants to come out as clouds and wants to come out as ice, and clouds and ice reflect more light, and so now you need even more CO2, and all of a sudden that's way more than anybody believes they ever had. So there's a big open question about how much atmosphere you need.
So is there
Yeah.
ever a chance we would have gotten a runaway greenhouse effect like Venus, or is we're just not nearly enough CO2 for that?
It seems like, yeah, so on early Mars, you need a lot of CO2 to get the greenhouse to a point where you can even have water liquid at the surface. To get to a runaway greenhouse state where the water is not stable as liquid because it is all evaporated into steam would take even more CO2. So that's a tall order. It seems like the histories of the two planets have been, of Venus and Mars, and the three planets, Venus and Mars and the Earth, have basically been dominated by the small size of Mars and the close proximity of Venus to the Sun. Because Venus gets a big boost just by being that much closer, having that much more sunlight to vaporize water and boost the Venus effect up. So people come up with all kinds of exotic ways to make the Mars atmosphere warm enough to have liquid water. The geology is not ambiguous. There was liquid water there. Maybe not oceans. So it's a problem for the atmosphere to have understand the else to what we know as we know. Yeah.
So you mentioned that most of the water on the surface is ice. Is
Yeah.
there liquid water? Do you know if there's liquid water underneath the surface?
Yeah, so there are probably liquid water as brines in places. So you put salt on ice on your sidewalk because that depresses the freezing point and melts it. If you have salty enough water, you can make it liquid at below temperatures close to the surface. At some point, it's just a question of how deep you want to go. Because as you dig into the planet, it gets warmer. It's not known for sure what the rate at which Mars's surface gets warmer with that. But people estimate that if you go a kilometer or two under the surface, there'll be a different. So maybe that's what happened, right? Maybe like there was life at the surface, and it got faster than the surface, so it just sort of followed the light, and all you need is an early surface of life, drill through the drill, and then light can speed up.
But it had a molten core at one time to hold that atmosphere in. So how do you take that into account? How do you know when that froze?
Yeah, so people do models using the frozen-in fields of the crust. They say we know how this rock behaves magnetically, and so we can tell how long it's been since it was magnetized.
So that was an actual measurement here. Probe.
Yes, you can measure it with a magnetometer orbiting Mars. Yeah. It would be really great to go get a piece of rock from a place that we know where it came from on Mars and bring it back. Because there is stuff in labs on the Earth that you can do that will never be done on put it on the roof, it needs to fit a shoebox. If you come back, you have the entire CU campus to do your research on this piece of rock. And that would tell us all sorts of things about exactly when these events occur. Yeah, so the InSight mission, which was delayed from launching, has been pushed back to 2018. That mission is all about these sorts of things. How much does the crust, what's the heat flux from the center of Mars, what's the temperature gradient as a function of depth, and is the core still liquid? Because that's an open question. You don't have a good idea about whether the core is solid. Certainly there was more magnetism in early Mars history than there is today. Yeah.
Is MAVEN going to study the methane issues on Mars?
MAVEN is not instrumented to study methane, so we're not really capable of addressing that question. But the trace gas orbiter, which is on its way to Mars right now, was in part designed to address this controversy and see whether or not there is methane there and measure its variability if it is variable. This is a huge topic of controversy in the science community. There are people who will swear up and down that there is absolutely no way that methane exists in the atmosphere of Mars. The reason why it would be super interesting, of course, is because it's produced on the Earth by life. Cows make a measurable contribution to global warming because of cow farts, which contain methane, which is a greenhouse gas. So it'd be really exciting if it were there because it's not predicted to be there. The photochemical models say that it should not be there in the atmosphere. But some people will put their hand on Isaac Newton's Principia Mathematica and say, I detected methane in the atmosphere of Mars, it's there. And other people will say, you're wrong. It's impossible, theoretically impossible. So we need better measurements, and that's what the trace gas orbiter is going to deliver. It gets to Mars later this year, so it should be really exciting once they start taking measurements to see what they see.